the recording. Uh, Again, I am telling this particular thing so that we missed it. Okay. So what I told you here, we see that whenever we are taking a solid material, the Misner's effect says that if the material is below critical temperature and we are giving the magnetic field that is below critical magnetic field, then the magnetic field is going to be repelled by the superconductor. That is your Misner effect. So here we studied the Misner effect for solid material. But in ring shape material, in where the material is having some hole type shape like that, then what happened there, the Misner effect is going to show some different behavior. So here what we did is that we took a ring shape material. First we reduced the temperature to below critical temperature. Then we induced the magnetic field, and we observed that here, even though the material is a ring shape material, there is a vacant space at the center. Still, throughout the area occupied by the material, whether it is a solid area or the vacant area, the magnetic induction magnetic field is not passing through it, and Misner's effect holds good here. But when we are changing the condition, like first we are reducing, keeping the material at a higher temperature than that of critical temperature and inducing a magnetic field, and then we are reducing the temperature below the critical temperature, then we are observing is that the only the solid region of the material is going to follow the Misner effect, not the center portion where the vacant space is present of the for the ring. There the magnetic induction is going to pass through as usual. Only the Misner effect will work at the solid region of the material. Then we observe that once we remove this magnetic field, there is still some current flow is there that is trapped in the ring. That is trapped in the ring. This current which is trapped here, that is called as your persistent current. Okay, this is called as your persistent current. So you can say that if a large current is induced by collapsing the field that maintain and trapped the flux, this is called as your persistent current. That means once we are letting the magnetic field pass through the material, after which we are reducing the temperature to critical temperature, then we remove the magnetic field. Then even if we remove the magnetic field, there is some current trapped in the ring shape of the material, that is called as your persistent current. And once again I am repeating it. If we are having a material, ring shape material, not only ring shape, remember this one, I am saying ring shape here and giving the example. I am saying any kind of material which is having a hole like structure in it. It might be a rectangular one, it might be an elliptical one, it might be a oval shape. Okay. I am saying some deformation in the material other than solid material. Solid material means what happens? Let us consider we are having a shot put ball or discus throw plate, disc. Those are your solid materials. There is no hole in it. But in ring shape means we are using the ring in our finger. So if you see that only the gold is present, only the ring per area, but there is a vacant space in there, no, where we are because of which we are putting it in on our finger. Like that shape is there. It might be a circular one or any other shape. In that case, this particular behavior is going to be seen. So here what we are observing is that here after inducing the magnetic field, if we are letting the temperature go below critical temperature and then we are removing the magnetic field, then there is some current is trapped in that ring shape of the material, that is called as your persistent current. This is one of the most important effect of your Misner effect. This is one of the result of your Misner effect. Okay, so this is what you have to remember along with your Misner effect. Okay, this is important for superconductor. Depending on this particular behavior, or depending on this particular thing on this Misner effect, we are having two type of material. Okay, what are those two type of material you can see here? That is your superconductor. We can say we are having two type of superconductor. So this is one is called as your type 1 and another one is called as your type 2, depending on its behavior. So first one we can see here, you see this red color line here, this is a total straight line that is proportional to each other. So if we are increasing the magnetic field, we are external magnetic field what we are applying, if we will increase the external magnetic field, the magnetization of the material is going to increase proportionally. That means if I am increasing the magnetic field by 2 units, then magnetization will also increase by 2 units. Okay, that is what is this straight line is representing. Okay, so in type 1 superconductor, what we can see here is that if we will increase the applied magnetic field, then the magnetization is also going to increase in the superconducting state. That means below critical magnetic field. As I told you, critical magnetic field and critical temperature both are representing, or transition temperature, both are representing the point where a material converts to superconductor, or we can say superconductor goes to superconducting states. Okay, that is what is your critical magnetic field. Now if we will be increasing the temperature, if we are having the magnetic field below critical temperature, then we are gradually increasing it. We can see that at critical magnetic field, suddenly the superconducting state is going to be vanished and normal state is going to be increased. That means if we will increase the magnetic field gradually in type 1 superconductor, at critical magnetic field, the magnetization of material will become 0. Okay, the magnetization of the material will become 0 and it is going to be go to normal state. But in case of type 2 superconductor, what we observed is that if we are in, there are two critical temperatures we will observe. Here two critical temperature, Hc1, that is your lower critical magnetic field, and Hc2 is the upper critical magnetic field. Now we are increasing the magnetic field here. When it reaches to the lower critical magnetic field, the magnetization value starts to reduce. It will start to reduce. It will not become 0 unlike your type 1 superconductor. In type 1 superconductor, when it reaches to critical temperature, magnetization becomes sharply reduces to 0. Directly it will drop to 0. But in case of type 2 superconductor, what we observed is that if the material is passing through the applied magnetic field, that is your lower critical magnetic field, it will start to reduce and then it will become 0 when it reaches to the upper critical magnetic field. Okay. So here we see the gradual reduction in the magnetization from Hc1 to Hc2. Okay. So before a lower critical magnetic field, the material is in superconducting state. After upper critical magnetic field, the material is in normal state. But in between lower critical magnetic field and upper critical magnetic field, the material will be in the mixed state. There it will possess both the property of superconductor as well as the normal material. Okay, this is two type of superconductors we are observing. Is there any doubt for this one? You can ask me. Put the message if you have any doubt. Timer did it. No doubt. Should I go for the next topic? Okay. Now you see, we will see the difference between type 1 and type 2 superconductor. Okay. See. So, as I told you, in type 1 superconductor, we are having only one critical magnetic field. Okay. The magnetic field externally whatever magnetic field we are giving, that is what we are talking about here. Okay. So we can say that the type 1 superconductor exhibit Misner effect in a full phase, but in case of your type 2 superconductor, Misner effect is holds good only below the lower critical magnetic field. Above lower critical magnetic field, it is showing both properties of normal material and superconducting state material. So we can say that this here the specimen is having. Give me 1 minute. Persistent current and induced current. Induced current means what you understand. Induced current means because of some reason the current is created by the material. Okay, but your persistent current is the current that is trapped in the material after a Misner effect. Okay, they both are similar but not same. Okay. Now you see here in this one we can say I'm continuing with the difference of type 1 superconductor and type 2 superconductor. Okay, so how it is trapped. So I think this thing you are going to learn again in your superconductor. There will be another means in detail chapter you will read in your higher semesters. Okay, so there I think you will be learning this one in detail. As of now, how much is necessary for you, I am telling that one. We will not go for more deep thing. Okay, so it will be of no use in future, in exam point of view also, in current situation also, because we need to cover the syllabus also, no? So let me see if I will get time after the class, then I will try to explain this one again. Okay, so we will see how it is trapped. Means there is a lot of mathematical calculation will be there behind this one. As of now, we only know I will only tell you this much, is that this is the effect of your this shape of the material. Because of the shape of the material, this particular thing is happening. Okay, and rest of the thing I will tell you later if I get time. But I don't think we are having much time here. Anyway, you are going to read again all these things in your higher semester. So let's see what we can do. Okay. Now you see here the types of superconductor. Two types of superconductor are there. So type 1, as I told you, in type 1 we are having only one critical temperature. Below that critical temperature we find the superconductor or superconducting state. Above the critical, not temperature, critical magnetic field. Above critical magnetic field, we find the superconductor. We find the normal state of the material. But in case of your type 2 superconductor, we are having two magnetic fields. One is your lower critical magnetic field and upper critical magnetic field. Below lower critical magnetic field, the material is acting as a superconductor. Above that one, above upper critical magnetic field, the material acts as a normal material. But between this lower and upper critical magnetic field, the material will show mixed state of superconductor and normal. That means both properties we can find depending upon the value of your magnetic field. Okay. These type of superconductor are called as a soft superconductor. Okay, because why? Because this superconducting material property of the material can easily be removed just by increasing the magnetic field or just by increasing the temperature. That's why these are called as a soft superconductor. But for type 2 superconductor, the superconducting state doesn't go very easily unless and until we are increasing the increasing the magnetic field above upper critical temperature. That's why that is what is the difference. So because of this particular state, because why these are called soft superconductor, because here only one critical magnetic field value is there. But in case of your type 2 superconductor, there are two critical magnetic field is there, Hc1 and Hc2, what we observed in the previous slide. This gap between this Hc1 and Hc2, that means the distance or the value of upper critical magnetic field is much higher than that of the lower critical magnetic field. So to overcome that distance, it is taking much more time and much more magnetic field. That is why there is a large magnetic field difference is there. So that is why these are not called as, these are called as your hard superconductor and these are called as your soft superconductor. Like in this one, we can see the type 1 superconductor examples are like lead, tin, mercury. But this type 2 superconductor are mostly the alloys which we are getting by mixing different superconducting materials. Okay, so these are having high electrical resistivity, and also that high electrical resistivity is going to be converting to zero once we reduce the critical magnetic field below the lower critical magnetic field value. Okay, so these are the difference between the type 1 superconductor and type 2 superconductor. Do you have any doubt here? Okay. I'm continuing. Whatever you have doubt, you can put in the box. Okay. I will try to clear your doubts. Okay. Now you see the types of the examples of superconductors, type 1 and type 2 superconductors with their critical magnetic field value in. Okay. So this is where your type 1 superconductor. Under type 1 superconductor, the examples are tungsten, zinc, aluminium. Okay. This is iron. In means indium. Okay, indium. This is mercury, lead, and the niobium. So these are the type 1 superconductors. For them, you can observe that the critical magnetic field value, that is only Hc value, is very low. You can see this one. It's a very low value we are having. And once we reach this magnetic field value, the type 1 superconductor, or if you increase the magnetic field value above this one, these type 1 superconductors are going to be converted into the normal state of material. But if we see the alloys of different material, the first one is the alloy of your molybdenum, lead and molybdenum, then and sulfur, then the magnetic field value, the Hc2 value, lower magnetic field value is much higher. For this niobium and germanium, the critical lower critical value of your magnetic field value is very much higher here. Okay, so it is, and this is only lower critical magnetic field value. The upper critical magnetic field value will be much higher than of this one. So to convert this type 2 superconductor into normal state material, it will be taking much more magnetic field value to make these materials into the normal state. Along with this, this one, this particular, all these materials is going to be associated with the critical temperature as well. And in among these materials, no material is having critical temperature above 0 degree centigrade. That means even we are not able to get even the room temperature, the value near to 0 degree centigrade. Room temperature, forget about it. We cannot go up to, we cannot achieve emit. We till now we have not achieved any superconductor that can work in your normal room temperature. Okay. Not always, huh? Mostly it is element only, because this type 1 superconductors only identified initially, means the first thing which we identified superconductor is the elements only. The type 2 superconductors are those things we developed. Okay, so mostly type 1 superconductor we find elements only, and type 2 superconductor we find is the alloys. Okay, now you see these are the examples I gave depending on the critical magnetic field. Remember all these materials which I have given you example here. We have given the example depending on the critical magnetic field value, either normal critical magnetic field value or lower critical magnetic field value. I have not associated them with the critical temperature. Okay, we till now we have not achieved any material that can be working as the superconductor in normal room temperature. Okay, so these are the different examples of a superconductor we have observed. Now we will see the high critical temperature superconductors. Those materials which are possessing high critical temperature, for them we will see. High critical temperature means what? The critical temperature for this mercury, what we observe, the critical temperature for this mercury was 4.2 or 4.3 Kelvin, I think. Okay, 4.2 and 4.3 Kelvin means it is very low temperature, and that low temperature we cannot achieve without either liquid helium or liquid nitrogen. Okay, so very low temperature, or whatever the temperature we are considering here for the superconductors, that is we are achieving at lower temperature. For both the things we need to find out the process how we will achieve the temperature, and mostly we are using liquid helium or liquid nitrogen for maintaining the temperature that is very low. Okay, so what we can see, if we achieve any material, we are getting any material which we can work, which is showing the superconducting property, that means zero resistance at relatively higher critical temperature, then we can find multiple use of those things. But that low temperature at which any material work as a superconductor need to be maintained either by liquid helium or by liquid nitrogen. Remember, liquid nitrogen. This liquid helium or liquid nitrogen, they are very costly, as well as working with this liquid helium or liquid nitrogen is a dangerous process also. Okay, they are very explosive in nature, so any little mistake, it can lead to a very big accident. That is what is very critical over here. So to make this superconductor work for us, or to use this superconductor, we need to get the temperature, of the critical temperature for the material. We need the higher value. Higher value means the more the higher critical temperature, the less amount of liquid helium or liquid nitrogen will be needed. Okay, so also the normal use, it can be increased in the case of your application purpose. Okay, so till now we have seen the critical temperature for type 1 type of superconductor is 77 degree Kelvin. Okay, and this particular temperature we can maintain in the with the use of a liquid nitrogen. Okay, and this liquid nitrogen is very dangerous also to work with. Okay. The next thing we will see the advantages of this type of superconductor. Okay, so we will see different examples now. Let me see. Okay, so these are different types of high critical temperature superconductors. We are having three types of critical superconductor with high critical temperature. One is copper based, one is iron based, and another is hydrogen sulfide. Okay, so copper based means the main material which we will use over here is copper. Till now, whichever type of superconductors we are using, they are copper based only. We are not using much iron based superconductor. Neither we are using this one, hydrogen sulfide. Hydrogen sulfide is quite difficult to work with actually. Okay, it is volatile in nature and first step, and to maintain the solid state of this one, we need to maintain the temperature at 203.5 Kelvin, that is below 0 degree centigrade. Also, at this particular temperature, the solid hydrogen sulfide is going to show zero resistivity. Okay, so this is copper based means the examples are like this is bismuth, strontium, calcium, copper oxide. Okay, so here BsCCO, what is written here is the first letter of all the terms which is used, not the symbols. Okay, bismuth, strontium, calcium, copper oxide, yttrium, barium, copper oxide, YbCO. Okay, these are copper based material and they are possessing little bit higher critical temperature. Similarly, for iron based, we can find these are the examples. Okay, I cannot name them. Okay, so these are the symbols we are using: Ln, Fe, and As. As arsenic, Fe iron, lithium, iron, and arsenic. Ln means lanthanum. Okay, Ln means the lanthanum, iron, and arsenic. Okay, these are the different type of high critical temperature superconductor. This is just for example I gave you. No need to remember all these things. Whatever I give you in the note, You remember that thing. So I will share you the note by tomorrow afternoon. Okay, you read that one, and if you have any doubt, you can just ping me in the WhatsApp. Okay, don't put message in Teams app after tomorrow or day after tomorrow. Once I give you the note, don't put message regarding doubt for this unit in that MS Team, because I might not be able to see your doubt, might not be able to clear it also. Okay. Next thing we will be seeing is the disadvantages and advantages of the high TC superconductor. Okay. Now you see, this is the advantages. Okay. If the critical temperature is higher, then it is little bit easier to achieve. Okay, if we can achieve the critical temperature for a superconductor at room temperature, that is also very nice for us. That is also very useful for us. Okay, so if the critical temperature is more than 77 degree Kelvin, it can be easily maintained using by the liquid nitrogen. Still, use of liquid nitrogen is not that much safe. We need to follow much more safety and precaution over here. Similarly, if the high TC superconductor exhibit extreme type 2 behavior, okay, extreme type 2 behavior means what? The superconducting state of the material cannot be removed very easily. Okay, and they are going to carry the large currents even in a very strong magnetic field. That is one of the advantages we can say here. Okay, because this is what is our necessity. If we can conduct the electricity with low loss of power, then it will be advantage for us. Okay, so we can use this type of superconductor, high TC superconductor, for power distribution network, which will be for high power distribution. What happened? We are finding loss of the power, more loss of power we can see. But if we use this high TC superconductor, that loss will be very less because of its high, because of its high current carrying capacity. Okay. And we can also use this one in case of your magnetic levitation. What is this magnetic levitation? I will tell you in the application part. Okay. Similarly, this high TC superconductors has its scientific, and if it is having this maglev, we can do easily, then it is going to find, we are going to find the application of this particular thing in many cases, many industrial applications, like your nuclear magnetic resonance and magnetic resonance imaging. These are the things we NMR will be going to, what we can say, that power saving. Okay, these are going to be helping in much more power saving, as well as this is going to data transmission, the communication what we are doing. No, that data transmission is going to be very useful, very effective. There will be no loss of communication will also be there. Okay, the information can be passed 100%. That is what is the application of this one. And this is also going to increase the efficiency of any kind of system, your either communication system or your power generation system. That is, the efficiency is going to be increased much more using this high TC superconductors. Then what is the disadvantages of this material? Why we cannot use these things in your day-to-day life? The disadvantages are like, this is very costly actually. First thing, we will find it very costly. To maintain the lower temperature, we need to use liquid nitrogen. That is also very, what you can say, dangerous to uh, uh, work with. Also, these compounds or these alloys what we are making, these are very brittle in nature. Okay, we can say composites or alloys. These are very brittle in nature. Because of their high brittleness, we cannot modify them into wire form. Okay, they are going to break very easily because of the lower strength in the mechanical point of view. Okay, because of the lower strength in mechanical point of view, we cannot use this one. We cannot makes the wire former with the required shape of the material, which makes its price much more higher. First, the manufacturing of the material is higher, then achieving the particular required shape is also getting very costly. Okay. And also because they are very brittle in nature, we cannot make them into wire form. That's why we cannot use them in electrical apparatus like transformers, generator or motors, because we need the wire winding over there. Okay, in transformer I show you copper windings are there, right? Copper wire windings. If wire is not there, or wire form that is getting very easily deformed, that form we will not get, then we cannot use it for the particular application. These two are the disadvantages of the material. Okay, these are the disadvantages. Now, okay, I will take 5 minutes more for this class. We will finish it up with the application of the material. Okay, application of superconductor. The application of superconductor is going to take 5 minutes or 7 minutes. 7 minutes. We will finish it up and then we will end the class. Okay. Now you see the application. The first application for this one we will see is your, as I told you, the magnetic levitation. Magnetic levitation means what? You must have heard about this maglev trains. Okay. In foreigns like in Japan, China, we are using these high speed trains, right? That is what is called as your magnetic levitation. So here what we are doing is that this high speed bullet trains you see, what we heard in our country by our prime minister, he is going to make this, he will bring this high speed train we heard in some years back. Okay, but that is not a concern here. We can see here this is a maglev train. Okay, here there is no wheel for this train is there, no wheel we are using. Okay, for this particular train we are not, there is no wheel is available. What is there? This train is going to float over this platform, that there are two rails you can see here, right? This train is floating on this rail. How? Because by using this magnetic repulsion and magnetic attraction, in taking these things into consideration. But when we are introducing this particular thing in your magnetic field, that means the throughout the material, the magnetic field intensity is going to pass, isn't it? That is going to affect the total system. But here what we are doing is that we are using this Misner effect, where that ring shape is there, no? In that one we saw that only the material, where the material is present, there only we can see the Misner effect. All the other blank spaces, there is no effect of the magnetic field repulsion we saw, isn't it? By using this Misner effect, we are going to use this material here. So here what they are doing here, they are using this electromagnet in the rails. Okay, also in the rail of the train. There is no wheel. Two rails will be there. The rail will be here and another rail will be here. Those two are the electromagnets. When current will pass, those two will convert into magnets, and they are going to repel and attract each other because of the, one is the Misner effect, another one is the effect of your magnetic field. Like if you may bring north pole and north pole, they will repel each other, and if you bring south pole and north pole, they will attract each other. Those two concepts they are going to use here, and by using that one, this magnetic levitation is due to Misner effect, and the movement of the train due to attraction and repulsion between the similar and dissimilar poles. Okay, this is what is actually the maglev train will look like, and this is what is the magnetic levitation, what we have seen, or what is actually we are using. Okay. You see, this is the globe we are having. This is a material which is a electromagnet, and this is also made up of a magnet. Now, when the current passes through this electromagnet, this becomes into magnet. This becomes a magnetic material. Now due to that there is a magnetic field is created. That magnetic field is going to repel this external magnetic field that is present over here. So it is floating over here. This is what is your magnetic levitation. Levitation means lifting up. Anything material is there, no, it is going to lift up by the repulsion forces. That is what is your magnetic levitation. Now if we can use that particular repulsion, that is what we have observed here in Mishner effect, then it is going to be very useful. And to maintain, if we can get this superconductor in our room temperature, then this price as well as the use of this magnetic levitation and magnetic levitated train is going to be increased manifold. Okay, not only in train only, but in many cases this magnetic levitation is going to work as a miracle, okay, or a magic. Similarly, what the second use of this one is high speed computer. Okay, high speed computer means what? The second application is your high speed computer. Now whenever we are using computers, you see where we are using this computers, no, many computers are there where we are maintaining the temperature to low temperature. Why? Because of this multiple work on the system, there is this communication is there, current is passing through each and every part of the computer, right? Because of which heat is generated. Why heat is generated? Because current is flowing means resistance is there, and for longer time if the current is flowing, the much resistance will be creating more heat. And to maintain the temperature lower, we are maintaining the surrounding temperature to the lower only. But if we get this superconductor at room temperature, that is going to work as, that is going to give a boost to your computer. Now because of the resistance of various elements, the computer is getting heat up and the work is getting slower. If there is no resistance, then there will be no heat generated. If no heat is generated, then no slow process will be there. Everything is going to work with a higher speed, and multiple times the speed is going to be increased. That is why we can use this one in case of your high speed computers. If we will get the superconductor at room temperature or relatively lower temperature which we can maintain without your liquid nitrogen or liquid helium. Okay. So again in this case of a transmission of power, the next thing we can say is your transmission of power, where we are seeing the transmission of power. Now you see we are having this high power transmission overhead lines, right? This overhead line, why they are generating very high heat, isn't it? Because of high power transmission, they are generating very high heat. Heat means what? That heat is nothing but the loss of power, because we know energy cannot be destroyed, it is only getting transferred. So that electric current power or energy is getting transferred into heat energy. That means some of the power which we are transmitting from one point to another point is getting transmitted, and some of the power is getting lost due to this heat generation. When we will get this this superconductor that we can use in normal room temperature or normal environmental temperature, this loss in power due to heat generation is going to be reduced, is going to be zero, not reduced, it is going to be zero. That means there is no power loss will be there. It is going to work as a, again it is going to benefit ourselves only, because we are using so much of generated power, we are using so much of system, but we can, if we can save it, then it is going to benefit for us. Okay, if you have any doubt you can put the message here right now, otherwise you can put message later also, so that I will clear it.